What we've done to our desktop process now is we've connected a large capacitor in parallel with a motor. The goal of this large capacitor is to electrically simulate mechanical inertia. By hooking a capacitor in parallel with a motor, what it does, it basically provides a load as we increase speed and a source of power as we decrease speed. It's analogous to having a heavy flywheel in that motor shaft. So when we increase and decrease the power sent to the motor, we see a slow rise in speed and a slow drop in speed. I can demonstrate that by going to manual mode and moving the output up. You can see the graph. You can hear the motor. I've moved the output up and it just slowly increases in speed. It's as though we have a heavy flywheel now attached to that motor shaft. I can move the output down and we see a nice, slow, gradual decrease in speed, like a large RC time constant. You can even see the curve right here on the graph as it gradually settles into its new speed. So what we've essentially done is change the time dynamic of the time constant of our motor process. Throwing this back into automatic mode, I can take my set point and raise it, and we'll see how this controls. You can see there's some oscillation here, and the period of that oscillation is substantially larger than what it used to be before we had the capacitor connected. Now, the fact that I have oscillation suggests to me that I might have too much gain. I can go in and change my gain setting down to 0.2 or so. Store that. Looks like I need to go down even further. At about 0.1. Further. There we go. So by lowering my gain enough, I can make this process stable. I can now increase the set point and see how it responds to that. And we see, again, a pretty slow increase in speed. I can slow this down with my finger. I'm going to find that it's more difficult to slow down than before. The energy stored in the capacitor really does act like a mechanical flywheel. It's like a form of inertia. I can slow this down and see the controller respond down here a little bit. If I increase the gain, let's say up to about 0.1 or so, whoops, a little bit too high. Let's go to about 0.1. There we go. When I slow down the motor with my finger, a little bit more aggressive action by the controller, and it tends to hold the speed a little bit more stable than before. You have to be very, very careful with integral, though, because with a slow-acting process, integral action will tend to wind up way faster than it should if it sees an error between set point and process variable. So if I turn the integral time constant down to where we had it before, which was about 0.003 minutes, we're going to find this is much too aggressive for this new process. We can see right away an oscillation begin to form because integral is looking at an error between process variable and set point, trying to take action on that error over time. Since we've now slowed our process down, it simply is not capable of responding as fast as it used to. So integral is way too impatient for this slow process. It's not to say that integral action is useless. In fact, it's very useful. It's simply that we have to have the appropriate integral time constant programmed in. So I'm going to change my integral time constant to something much slower than what we had before. I'm going to store that value there. Immediately got rid of the oscillation. It's very slowly, gradually taking care of the error, changing the output until we finally get down to where our set point should be. Looks like I can go a bit more aggressive on that, so I'm going to decrease my integral time. I'll give it a set point change. We'll see how it responds to that set point change. That's a pretty fast response to set point. I can increase set point again. And we can see here how quickly it levels off. That's pretty respectable control out of this system. And if I slow it down with my finger, placing a load on the system, it'll slow the motor down a bit, but then the controller kicks right in with additional output and tries to bring me right back to set point. It does a pretty good job of that. When I let go of the motor shaft, it will overspeed briefly and then correct. But we don't see any undue oscillations. In fact, it looks like by the slow approach of my process variable, I can probably have an even more aggressive integral time constant. So I'm going to try this right here, cranking a little bit more integral, which is a little bit less minutes per repeat. Now if I slow it down with my finger, it responds quicker. It tries to keep it to set point much more aggressively than before. If I let go, it overshoots and then comes back to set point quite rapidly compared to what it did before. But it's interesting to show how we can connect an electrical component to the motor like this and electrically simulate a mechanical effect such as inertia, and then see the effect that has on the process dynamics and how we must retune the controller to compensate.